In this quick video, I want to talk about how we go about using these techniques and these tools in practice. So how we actually account for the presence of spatial autocorrelation and apply the statistical test. In regional economics, we often talk about the mechanism through which nearby regions influence each other. These are theoretical questions, and they're interesting in their own right. But before we can actually model these effects and test them statistically, we have to answer a simpler question. Is there actually spatial structure in the data, or are we just seeing random variation across space? In standard econometrics, we assume that observations are independent. I've said that several times in this module already because it's very important. Because in regional economics, it's rarely true. Think about housing prices in neighboring counties or unemployment rates across metro areas. They're not completely independent of one another. This means that there's some spatial autocorrelation going on, where the variable in one location depends on the variable in nearby locations. So we need to test for and measure the spatial autocorrelation before we can do any real empirical analysis. The most widely used statistic for this purpose is Moran's I. It measures how much of a variable is correlated with itself across space. So positive Moran's I mean that nearby regions have similar values for whatever variable you're looking at. So there's evidence of clustering. Negative Moran's I means that nearby regions have the opposite values, that there's dispersion. And zero, which is exactly in the middle, means that there's no systematic spatial pattern at all present. It's completely random. And Moran's I, the value that you estimate, runs between -1 and 1. So -1 is that perfect negative dispersion, and +1 is complete clustering together. Now, before Moran's I was adopted, people used Curie C. This was a similar measure. It's not too commonly used anymore. It wasn't limited to between -1 and 1, so the number could be quite large. But it told you the same basic thing. Now, once we measure Moran's I, how do we know whether the observed pattern is statistically significant? So Anselin emphasizes permutation testing, which is a non-parametric approach. Basically, what we do is we repeatedly randomize the values across the map thousands of times, recomputing Moran's I each time to see how often a value as extreme as our observed statistic would occur by chance. If our observed Moran's I falls in the extreme tails, we can reject the null hypothesis of no spatial autocorrelation. This randomization framework became the standard for spatial analysis because it doesn't rely on parametric assumptions or on normality. Now, Anselin also shows the limits of global measures like that global Moran's I. A single number like Moran's I can't tell us where the spatial clustering is happening, only that it exists. So the local indicators of spatial association, these decompose Moran's I into local contributions. With this, you can identify the regions specifically that are driving the clustering and see where they're occurring in space. There's several types of spatial models based on where we detect the spatial autocorrelation to occur. To determine which one to use, we use Lagrange multiplier tests to help decide whether to use a spatial lag or a spatial error model. This is something that is more of a concern for later than for right now, but just to give you a little bit of a preview, we use a spatial lag model when there's spatial autocorrelation present in the dependent variable, and a spatial error model when the spatial autocorrelation is present in the error term. So we would use this instead of the standard regression that assumes independence between observations. Either the spatial lag or the spatial error will be able to capture that spatial autocorrelation and account for it. So just for a quick conclusion, spatial data are rarely independent, and spatial autocorrelation tends to be the rule, not the exception, when we're looking at regional economics types of questions. So we need to be able to test whether spatial autocorrelation is present and identify which observations are causing it. From there, we can test to use the appropriate model based on where the spatial autocorrelation occurs.